Okay, today we're going to go ahead and get started with the new unit, which is on chemical kinetics. I'm going to start talking today about rates of reaction. Okay, so rates of reaction are ways of looking at how fast a reaction goes. And we talk about the term rate. In chemistry, we're talking about the speed at which a reaction works. Now, we've talked a lot about stoichiometry and equilibrium, which tells us what we have and what we're going to have. And equilibrium tells us the quantities we'll have when we get to that equilibrium principle and various manipulations, but we never answer the question of how fast does it take to get to that point? And that's what chemical kinetics is all about. If we're going to talk about studying and understand a chemical reaction, we need to understand the stoichiometry, the thermodynamics, which is the next topic we're going to talk about. We need to know something about the equilibrium and the kinetics. So we have to look at all of these approaches if we're going to talk about synthesizing chemical reactions. So this specifically is talking about the speed or the rate at which a reaction occurs. Now, what a rate is, you might remember from physics, is a change in something per unit time. So most of the things you looked at in physics were changes in distance over a time interval. Well, in chemistry, we're not going to look at that. We're going to be looking at a change in concentration over a time interval, okay, or how much of a reactant is left over. We can also do this through pressures, okay, so pressures and concentrations are two ways of looking at this. Now, one thing to mention here, and this is something you really want to remember, is that you cannot figure any of this stuff out by looking at the balanced equations. This is something a lot of students fall into a trap in, but the rates have to be experimentally calculated. So what that means is that you're going to have data tables and you have to use experimental data to figure out these rates of reactions. Now I'm going to show you a couple ways of doing that. There's two ways, which one is known as a differential rate law, which I'll talk about in the next video, and then the second method is what's known as the integrated rate law, where you take the differential equation and integrate it. Again, don't worry about the calculus part, but that's essentially what's going on. All right, enough of the foreshadowing. Let's get to the rates of reaction. So let's take a look at what we're talking about here. I guess I should probably talk about the units. So if we're talking about a change in something, in this case the moles, we want to look at how many moles change per given time. So if you have a chemical reaction occurring in a container, well, you know that you're going to have a volume for the container, and you're going to have these gas particles, or particles that are in here. You could also have a solution. Okay, remember the solution would be the volume, so you could say the volume of the solution. So you can see that we can look at a change in pressure or a change in concentration. Molarity can change, or our pressure can change. Now we typically look at these as molar per seconds, but you can look at it as pressures per second, because as these particles disappear and get used up, the pressure is going to change, because we know that the moles are connected to pressure. Anyway, so we're looking at moles per the volume of the container, whether it's gases or solutions. So we summarize, or simplify that as molar per second. Molar per second. It could be per minute, could be per hour. And what we're looking at is the rate. So we're looking at how this concentration, remember the brackets, these brackets here mean concentration, so we're going to talk about molarities. A change in the concentration as the time changes. So therefore we have a delta concentration and a delta T, and that's what we're essentially looking at. Now, one thing about these units on the AP test is they sometimes write it like this. So don't be confused if you see this unit here, molar per second, written like this. Sometimes they write it as moles per liter per second. So that would be this first one here. So these are all the same thing, as this would be equal to molar per second. Okay, so just a little bit something about the units there before we get too involved. Alright, so let's take a look, for example, the decomposition of nitrogen dioxide. Okay, so we're looking as we want to kind of talk about how fast this reaction is undergoing a change or a decomposition into the nitrogen monoxide and the oxygen. Well, we're going to talk about ways of experimentally collecting this data when we do some experiments for kinetics. What we do is we measure some time intervals and we measure the concentration. So it looks like here every 50 seconds they measure the concentration of the nitrogen dioxide from 0 to 400 seconds. And then they did the same thing for the nitrogen monoxide production and the oxygen. So if we take a look at this data, we can see that the concentration of the nitrogen dioxide is going down, while the concentration of the nitrogen monoxide and oxygen are going up. And that's important because these are your products and this is your reactant. Since this is your reactant and these are your products, this is what's going to be called the rate of disappearance. these concentrations are going to be going down, so we're going to have a negative change in concentration of the nitrogen dioxide because it's going to be going down. While over here, our nitrogen monoxide concentration is going to be going up. So our change in concentration here is going to be positive. Okay. Now they're not going to necessarily be equal to each other. I'm going to get to that in a little bit and how these two are related to each other. But that's what we're looking at. How does this change over a time interval? And we can do that using the graph, right? So we can see that the concentration of nitrogen dioxide decreases as time increases, right? Because that's what the data shows. Nitrogen monoxide and the oxygen increase as time goes on because they're being produced. So a rate of appearance and a rate of disappearance. Now, one thing to look at with this data is notice that this isn't a straight line. This decomposition of nitrogen dioxide is not constant throughout the whole thing. So this rate is constantly changing. So if I were to look at and calculate the average rates, and that's what we would look at, an average rate would be, let me back this up here just to explain what an average rate is real quick. An average rate would be if we were to take, from this point here to this point here, and we were to look at what the average is. That would give us a straight line, but that's not what we want. We want to see that the change is going to be different as we go through the line here, okay, through the curve. So let me show you here. So what they did was they figured out the average. So from 0 to 50 seconds, what was the average rate of nitrogen dioxide? Well, it wasn't always that, but overall, if you look at that 50-second, breaking it down to 50-second intervals, we can see that the rate changes throughout. So our average rate is changing. So the problem here is that we have the reaction's changing and the rate is changing as the reaction goes down. And that's important because it makes sense if you think about it, because as the nitrogen dioxide gets used up, there's less and less of it to react. So it makes sense that as the reaction progresses, we have a lower rate because we have less nitrogen dioxide. We're going to talk about that again later when we talk about what's going on and why we think these reactions are doing what they're doing. That's going to come in with the collision theory at the end of the unit. So our average rate shows us the rate of change over a specific time span. Okay, not very useful, but we're going to fix that in just a little bit. Okay, so average rate of reaction. What we can do is we can experimentally figure that out based on what we're doing here. So that's what this was here. We could figure out these rates using the experiments, right? That's what we're doing. From 0 to 50, that would be the rate of the reaction at that particular point between the first 50 seconds. The next 50 seconds, this would be the rate, and as you can see the changes we go throughout, and it keeps changing. So what we can do is we can use the balanced equation. Take that back. Once we have the balanced equation, we can make some connections between these two rates. So far, we're looking at the rate of disappearance of something called C in this reaction. I should take that back. It's the rate of appearance because it's positive. The rate of disappearance of A because A is a reactant. So we can focus solely on one substance at a time. Okay, we look at the rate of C, how it's being produced, and the rate of A. Now, because it's a balanced equation, these two have to be connected to each other, right? A and C have to be connected to each other based on the stoichiometry, based on the coefficients that are in here. Okay, so we can take the average and figure out this stuff here. And then the last part here we're going to look at is once we've experimentally determined the rate, okay, so we've experimentally figured that out looking at the data, we then can use the balanced equation to figure out the rates with respect to the other substances. Okay, so I know this kind of seems like it's a little misleading from what I said before, but think about it. We already used the experimental data to figure out the rate of concentration change of this, right? How did this change? Well, if I know how the coefficients work out, if this gets used up by 2 moles, I'm going to get 2 moles here. And if my rate is the change in concentration, right, of the nitrogen dioxide, well, the concentration is, the volume is going to be the same, so the change in concentration is really based on moles because it's molar per second. Molar is moles per liter, and the moles are going to be what's changing. So if the moles here decrease by 2, this goes up by 2. So the rate of disappearance of this will be equal to the rate of appearance of the nitrogen monoxide. So they're produced and consumed at the same rate. Oxygen, on the other hand, is going to be produced half as much as the nitrogen monoxide. So as this is being produced at half the rate. So it's going to be being produced half as fast as the nitrogen monoxide. and we can see that we can compare nitrogen dioxide to the oxygen, and that's what we're doing down here. So we can do is we can take this balanced equation, and once I figure out one of these rates, if I know what the rate is at this particular point in the experiment, I can then figure out the other two. So with that data here, it really didn't have to calculate and measure all of these. What I could do is I could determine it from this rate based on this. I could then figure out what those two will be based on the stoichiometry. But I have to get some sort of experimental data here. Really, really important, guys, that you pay attention to that part, is you have to have the experiment. So we'll look at a little bit more of this in class, but this is your introduction to rates of reaction. Take a look at the next video on differential rate laws and how to calculate them. All right, thanks a lot.